Cal 2, all right? So you've got to have Cal 1 like nailed down completely. All right? It's like literally it's like you have to learn how to walk before you can start going backwards, right? If you can't walk, you're not going to go backwards. Yeah. Well, it's kind of like Cal 1 is robotic, right? Cal 1 is very mechanical. I say mechanical. Cal 1, we give you formulas. Like, here's formulas, and they're like, okay, and you get good at them. And in Cal 2, there aren't formulas. It's more like techniques, and you try them, and you're going to make more. In Cal 2, you fail more times than you succeed when you're doing problems. Like, you start over. You start problems over. 10 minutes in, you start over. 10 minutes in, try something different. So persistence. All right, I hope I'm not like just dissuading you from this. I'm not trying to like be negative. I'm trying to be real. I don't want to lie to you, okay? The calculus sequence is hard, all right? It's hard. And I know some of you like just want to go on to medical school or something like that. They keep upping the math requirements, right? They keep doing that that's how you weed people out, but that's not my choice. So, look, persistence, right? You can do it. How do I know you can do it? How do I know you can do it? Because I did it. That's how I know you can do it. That's not good enough reason? No?
What's the highest math?
Well, math is not linear. So like normally when we think of math, we think there's like this class followed by this class followed by this class. Math is like a tree, right? So y'all are all still in the trunk of the tree, right? There comes a point where the math starts to branch off. And so you go down certain paths. And so I went down my path, the path I went down. So there's not like, calculus 10, you know what I mean? It's I'm not going to get into my whole long story because I remember as a student it would bore me when my teacher talked to me about them. But I will tell you this. I was not a gifted math student in high school. I was not the top of my class in math. I failed classes, okay? I started college. I had to, start further back. And I'll just sum it up. You know what it comes down to? Work. It comes down to work. You put the work in, you're going to get the reward. If you don't want to work, don't waste your time. Don't sit there and say, I want to be an engineer, I'm going to be an engineer, and not be willing to throw yourself into this. You have to look at yourself in the mirror, and only you know if you're being completely 100% invested in what you're doing, right? Only you know that, right? I don't know that, and for me, for a long time, I wasn't being 100% into school. So once I got serious and realized I was up against all these other students that were way ahead of me, I figured, you know what I'm gonna have to do? I'm gonna have to work harder. I'm gonna put more time in, and that's what it took. So, I started off in college, I struggled with this as well, So when I'm sitting up here and I'm showing you all this, don't assume that I was just always good at this. Like, it took a lot of work to get to this point. So that's why I know it can work, it can happen for you as well. You just have to be willing to put in time, okay? All right, so here we go. We have a complex fraction. This is number 76. We have not seen anything like this before. What makes this different than the ones before is that if you look back at the problems we did, this was a fraction and this was a fraction, so we could just do like a keep dot flip, right? We just did that thing. Can't do that quite here because this is not a single fraction. It's two things being subtracted. So we need to first put this together into one fraction, this together into one fraction, and then we could do the flipping. But you got to put them together first, right? So let's put these together. I'm going to just rewrite this as over 1 and then over 1. So on this first one, on top, I'm going to multiply by a 1 here and a 1 here so that these two have the same denominators. So what's missing? On the 4 over 1, what's missing over there? What do I need? I need x squared on top and bottom. And then over here, I need what? 1 over 1, right? There's nothing. I actually don't even need to put that, do I? Can we take care of the bottom while we're here? Do you mind if I look at that? Kind of kill two birds with one stone here. So I have a 1 and an x squared here. So I'm going to need x squared here. And then here again, 1 and 1. I didn't necessarily need that, but I'm just trying to stress again that I'm trying to get a common denominator. All right, let's do this. I'm going to put this together. I'm going to put this together. So I should get 4x squared over x squared plus 1 over x squared. Then over 3x squared over x squared, minus 1 over x squared. Okay, that's just me putting those together, the things I circled, right? I just multiplied these out. Right? And now that they have the same denominator, I can just take this and add. So that'll be nice. I don't have to worry about anything nasty there. Just add them. And then over here, now, can I do the keep dot flip thing? Yes? I can leave this fraction, the top fraction alone. I can take the bottom fraction and flip it. And that allows me to get rid of the x squareds. And then what's left here, I can't do anything else with. Questions? We still have more. This section is a grind. But we're just going to do one more problem, and then we'll be done with R7. R8's going to go a little faster. So, no questions here? All right, so let's do this. 4x in parentheses here plus 1, that quantity, times 5 minus 5x squared, or sorry, 5x minus 2 times 4 all over 5x minus 2, that quantity squared. So in the instructions here, it says, do y'all see in the ebook here, do you see this little symbol? Do y'all see that right there? That symbol means the reason they're giving this to you is because you're going to see things exactly like this in a calculus class. So these are problems taken. This is just like one little intermediate step of a calculus problem. So they just want you to just, again, make sure you know what to do with this algebraically. All right? So simplify it. So there's stuff we can do here. This is not a super complicated problem. Like the one we just did, we had to get a common denominator, put things together, flip. This one, just distribute the 5 here and distribute the 4 here, right? And then we'll subtract them when we're done. So I distribute the 5 through, I get 20x plus 5 minus, now you have to be careful with how you do this. This is going to be 20x minus 8 all over the 5x minus 2 squared. So the thing you have to be careful with is this minus sign. If you're going to distribute the 4 through to these two, then if you're going to wait on this minus sign, then just make sure you put that in parentheses. Then distribute your negative through. Y'all see what I'm saying on it, or no? Yeah? No? Who said that?
So you can distribute when the 5's on that side?
Yes. Yep, absolutely. When we learn distribution, right, when we learn to distribute something, we normally have the 5 in front, right? And we just go 5 through, but this is just multiplication, right? That's all it is. Well, multiplication is commutative. So if you reverse it like this, then it just goes that way. Same thing, same procedure. All right, so now I'm gonna pass that negative through. It becomes a plus 8, right? Minus 20x plus 8. And then all over 5x minus 2. Squared, almost done. Collect like terms on top. The x terms are gone. 13.
Is that it?
That's it. Yep, that's it.
I know this is a really different question. I'm going to ask it. What do I do with the 5x to the second power?
You don't have to do anything with it. You could, if you want, multiply it together, but you don't need to do that. So you're done. Your answer is just an algebraic expression. All right, that wraps up, finally, the review of rational expressions. So if you have polynomials that are being, divided together somehow, that's what we're doing here. We just reviewed on all the different sort of things you run into, all right? Can we keep going? You hanging in there? We're going to review R8, review section 8. This has to do with roots and rational exponents. So let's just make sure we get some of the fundamental ideas here down. Again, I'm going to assume that you've seen some of this, most of it, all of it, before at some point in your life. And I'm not here to try to insult your intelligence. We all know what that means, right? How do you say that? Square root of 4, right? And what's the answer? 2, right? So the reason that's the answer is because when you take 2 and you square it, you get 4, right? What we have out here is a 2, but we never write that, right? We never write the 2. It's understood to be a 2. But that's different than me saying this. Cube root of, I'm sorry, that's not cube root. That's 8th root. The cube root of 8. The answer to that would be 2 as well. Why? Because when I take that number 2 and I cube it, right, when I do the cubing of that, I get the 8. Right, so we've seen this, yes? And there is another notation, right? When you take the nth root of something, right, that's called radical notation. It's called a radical. But there's another way I could have written it as x to the 1 over n, and that's called rational exponents. So we can either use radical notation or we use rational exponents, meaning that the power up here is a fraction. So if I write the square root of 4, right, that is the same as me writing 4 to what power? The 1/2 power, right? That's this right here. If I write the square root of 4, there's a 2 out here. This property says we're taking this x and raising it to 1 over n. There's more to this formula. If you have the nth root of something to a power, then that is going to be the power over, you basically make a fraction out of these two numbers. So this right here becomes the numerator of the fraction, and this becomes the denominator. How many of y'all this looks familiar? Like you did see this at some point, yes? Okay, again, rational exponents, radicals. In calculus, we almost exclusively work in rational exponents, almost exclusively. So, and there's a reason for it. You'll see when you get to it. There's a reason. It just makes life easier for us to work with it here. In this class, we want to be comfortable going, both ways with it. We need to be comfortable here and here. All right? So, let me ask you, just before we get into these examples, What if I put the cube root of x squared? Can you rewrite that as a rational exponent?
Yeah.
Yes, what would it be? X to the 2/3, right? X to the 2/3. But can you actually simplify that? Can you do anything with this? Let me put something versus this one. Which one of those can you do something with? The one on the left or the right? The one on the right. And the reason we can do something with the one on the right is because this number is bigger than or equal to this one. See this number smaller than that? If this number is smaller than that, you can't do anything with it. But for this one, we could write it this way. We could rewrite x to the 4th as x cubed times x, right? And then we could break this radical into two radicals. Like that. We can break it into two radicals because there's multiplication in there. We can do that. And then what is this equal to? X. Just x. If you take x and cube it, then you take the cube root and the cube kill each other off, and you just have x. And then in here, or this one, is still cube root of x.
The exponents just slaughtering each other.
Yeah, they're just getting rid of each other. Yep. So you can change this to be this, right? But you can't do anything with this because this number is smaller. Any questions there? Sure. One last thing, then we're going to do examples. How about this? Can you add two radicals together? Not these, right? What's the only way you can add two radicals together or subtract two radicals? What's underneath the radical has to be exactly the same, and then these radicals have to be the same, right? So these are both square roots, right? We would need either both of them to have 3 underneath or both of them to have 2, and then we could add them. So let's just do that. Let's change that. What would this be? Well, look at it like you have an apple plus an apple. That's 2 apples, right? So you have 2 of these root 2's. Let me do another one. Root 6 plus root 6 is 2 root 6's, right? That's how you add radicals. How about, let me do this. Root 12 plus root 2. Can we add those together? Oh, wait, hold on. I meant to make this a root 3. Can we add those together? It doesn't look like we can, does it? Doesn't look like we can? But we actually can. Why? Let's see. Root 12 can be rewritten how? Root 4 times 3, right? That's 12? And then here you can split that into 2 roots. Root 4 times root 3. What's the square root of 4? 2 root 3, right? So this really turns into 2 root 3 plus root 3, right? That's really what that is. It's kind of hidden. That 12 hides it. But this 12 is actually 2 root 3. And now we're adding to it a root 3. So how many root 3's do we have? 3 of them. This is 3 root 3. Okay, this is just a reminder of how we add and what radicals are, how we add them, right? So let's see what problems we have here. There's not many from this assignment. Let's look at number 42. 42 is 2 root 12 minus 3 root 27. We're asked to subtract these radicals. Initially, when we look at it again, we say, okay, well, these aren't the same, right? So we can't add or subtract them. However, we need to make sure we can't simplify them. So let me see. I think about 12, and we just did it, right? It's 4 times 3, right? This right here. So we know that this is going to turn into what? 2 root 3, right? So I have a 2 out here already, and then this piece right here turns into 2 root 3. I'm not showing that work because we just did it, right? Can we do something like that for the 27? 27 is 9 times 3, isn't it? I'm going to do that on the side over here. Root 27 is the same as root 9 times 3, but that's the same as root 9 times root 3, and the square root of 9 is 3. So 3 root 3, right? That's what that is. So root 27 is 3 root 3. I can put that right here. There was already a 3 there, and then 3 root 3. Any questions on where I'm getting those from? Like this right here is this, right? And this right here is this. This 3 is here, this 2 is here. We're not done. 2 times 2? 4. So we have 4 root 3s, and we're subtracting from it what? 3 times 3? 9. 9 root 3s. What's 4 root 3s take away 9 root 3s? Negative 5. Negative 5 root 3s. That's it. Trying to see if there's one like number 51. There's really not one like 51 unless I do 53. 53 is pretty bad. Let's do 53. That's if we do 53, I think the rest of them will be okay. We've got what, 9 minutes? Okay, cube root of 16x to the 4th y minus 3x cube root again 2xy and then plus 5 cube root again of negative 2x y to the 4th. All right, we're going to try and simplify this. In order for us to add or subtract these roots, what's underneath the root has to be identical in each one of these, right? These are not identical, are they? Maybe there's a way we can make them identical. So let's start with this right here. We're doing cube roots, right? Not square roots, so be careful. Cube roots. So I need to know something about my perfect cubes. Do y'all know what the perfect cubes are? What's 1 cubed? 1. 2 cubed? Oh, that's squared. 2 cubed? 8, right? 2 times 2 times 8. 3 cubed? 3 times 3 times 8. 27. 4 cubed? 64. 5 cubed? 125. Okay, after that, who cares, right? So I recognize right here 16 has 8 in it, right? Because I'm thinking cube root, so I'm thinking 8. So I'm gonna rewrite this as, just watch me do it first, as 8 times 2 times x cubed times x times y. So what I did there is I realized that since I'm dealing with cube roots, I'm going to use 8 because 8 is 2 cubed. 8 times 2 is 16. The x to the 4th has a 3 in there, right? So I rewrite it as x cubed times x. That's x to the 4th, and then I have a y. That's just preparing me for the next line, which is to actually take the cube root of 8, and then what's the cube root of x cubed? It's just x, right? Well, I'll do that in the next line. Minus 3x cube root, okay. I can't do anything here. 2 is not a perfect cube. X doesn't have, there's not 3 x's in there, and there's not 3 y's, so I'm just going to write 2xy. And then plus 5, okay, cube root. Over here, is there anything we can do?
Y.
Yeah, we can break that y down. Let's do negative 2xy cubed times y. All right, I'm doing that so I can do the next line. All right, what's the cube root of 8 was what? 2, so that comes on the outside of the radical. The cube root of the x cubed was an x. That comes outside on the outside of the radical. So I've taken care of this one and this one. What's still under here? 2xy. So that's going to be underneath the cube root. And that gives me some indication of what my common radical needs to be. Cube root of 2xy. Isn't that what I have here? Cube root of 2xy. So this is going to be minus 3x cube root of 2xy. And then on this one, let's see what happens here. I can do the cube root of y cubed, which would be just a y outside with the 5. There's a very important step here, and let's see if anyone can figure it out. I've taken care of the y cubed. I need this to be what underneath here? 2xy, not negative. Can you take a negative out? Yeah, because you could look at it as a negative 1, right? What's the cube root of negative 1? What's the cube root of negative 1? Not the square root. What's square root of negative 1? I. That's I. We're not talking about I. Okay. Negative 1. The cube root of negative 1 is negative 1 because negative 1 times negative 1 times negative 1 is negative 1. So that means I can take this negative 1 that's here and bring it out as a negative. So I'm going to change that plus to a minus. That took care of this negative sign here. That leaves me with a 2xy. This is the review of radicals. I understand it's like if it's been a while, this is going to be like, what? All right, now can I put all those together? Are they all like radicals? Is this the same as this? The same as this? Yeah, they're all the same, aren't they? So if these were just numbers, right? If it was 2 of these minus 3 minus 5, you would just add the numbers together, wouldn't you? Because these are not just numbers, what we're going to do is we're still going to take these things and add them together, right? And I'm just going to write it down. What's 2x minus 3x minus 5y? All of that, whatever that is, whatever that adds up to be, is sitting in front of the cube root of 2xy. And you can do something there, right? Negative x minus 5y. You have to have in parentheses, sitting in front of the cube root of 2xy. So you're essentially putting like these are like coefficients, and you're adding all your coefficients together and putting that in front of your like radical. All right, I think that's probably where we're going to need to stop. We're not done with this section. We need to do rationalizing denominators next time, and then we'll get into 1.4. So we are a little behind, and we're just live with it. All right, I'm not going to like speed up just to catch up right now. Your homework is to finish R7 if you haven't. If you've already done it, great. But then also for R8, at least go up through number 51 for R8. Got that? For R8, just through 51. If you can go past that, go for it. But I will come back. We'll start class. We'll do 55. We'll do a problem like 55, 61, 67, and 73. And then we will move on to 1.4. Pardon me? Say again? Did you come in late? Oh, I don't have time to like do it, so we'll have to work something out. Are you available to come to my office hours at all? Ever? They start today at 12:30 and they go till 2. But check the syllabus. If you can come into my office hours, I'll let you have that. But you only get one of those per semester, so, like one retake. So try and be on time. All right.